Okay, second video, starting from page 4, the complex number system. Now that we've learnt what an imaginary number is, we should just get straight into what a complex number is and what the rules are for working with complex numbers. Now, you've already seen these. Basically, everything I'm going to do, you've seen in John and Betty video. Okay, but we're just going to formalize it. So the name complex number is just the name given to a number that can exist with both a real part and imaginary part. So it's like complicated. It's got a real bit and an imaginary bit. It's complex. For example, the complex number 3 plus 4i, the real component is 3, but the imaginary component is the 4i. Complex numbers in general are referred to as this: z equals x plus, z means complex number, pretty much. It's the letter, pronumeral, we assign to a complex number, and it's of the form x plus yi, or it can be a plus bi, c plus di, whatever. All this means is that the complex number z is made up of the real component, in this case the x, and the imaginary component, in this case the y. Well, I suppose it's yi, but the x's and the y's aren't anything special, but please be careful, x and y must be real numbers, okay? So they can be something like square root of 5, that's a real number. So they can be fractions, remember a real number can be a whole number, a fraction, or a third square root of something, all right, or pi or something, as long as it's real is anything but imaginary, all right? So a real number, now the x's and the y's are just real numbers. A real number multiplied by I is imaginary. Look, y is real, and once you multiply it by I, you get imaginary. So once you put an I next to something, it's imaginary. That's the imaginary bit. So a real number multiplied by I is imaginary, and a complex number is any number with an imaginary component. So if I just say my number is 2, that's not complex, because it's just got the real bit. 2 plus 3i is complex, because it's got an imaginary part. I could just have 3i. That's got an imaginary part. The real part's just 0. See, 0 plus 3i is still complex because it's got an imaginary part. So for it to be complex, it must have the imaginary part. Okay? So a real number multiplied by I is imaginary, and a complex number is any number with the imaginary bit. Anytime you see something I, that's the imaginary bit, but that therefore makes up a complex number. All right? So the real component, we write it like this: RE bracket Z. And the imaginary component is expressed as imaginary bracket z. So if I give you the complex number z equals 6 plus 2i, then I say, if I'm asking you what's the real part of that imaginary number, I go real part of z, re bracket z, is the 6 bit. And the imaginary part of the z, so instead of writing imaginary part of z, I just go imaginary bracket z, is the 2. I don't have to put the I, because they're just asking for the bit in front of the I. Okay? So the imaginary is the 2 because it's in front of the I. You don't write 2i. Okay? So, 2 complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. That's just common sense. So in other words, it's really basic. If a plus bi equals 5 plus 6i, then doesn't it mean that a is 5 and b is 6? Can you see that? So if a plus ib equals 7 plus 3i, then a is, these are easy. What's a? Compare them, they're the real bits. 7, b is 3. The next one, a is 2, b is negative 6. The next one, a is negative 3, b is, and a is, be careful, the root 3 on 2, that's still real, okay, and b is, good, because there's a 1 in front of that I, and b is a half. All good? Over the page. Now, addition of complex numbers, you saw this with John and Betty. A plus bi plus c plus di, basically just add the a and the c, and just add it's just like algebra, and just add the bi and the di. So you don't have to write it all out. So what would this be? Isn't it just 2 you're going to be doing 2 plus 6 plus 3i plus 8i. I've just put all the real bits together. You don't even have to write that. What's the answer, girls? 8 plus 11i. The next one, you can write it all out if you want. 3 minus 4i plus 2 minus 5i. What do you get there? You get 5 minus 9i. This is 8 plus 6 minus 5i plus 3i. These are just really basic. What have you got? 14 minus 2i. It's just like algebra. 6 plus 4i plus 6 minus, sorry, I forgot to put them together, minus 6i. What do we get? 10, 12, minus 2i. Good. Okay, really basic. Now, subtraction of complex numbers. See, we know how to add complex numbers, but look, subtracting is just the same, but they have a complicated way of saying subtraction. Subtraction of a complex number, it's called the additive inverse. So, if we put back up, where am I looking? Where have we got? So we know that, for example, when you add, just looking at this first bit, a plus bi plus c plus di is, we add the a and the c and we add the b and the d. But if we put this c, write this c, sorry, as negative a, and this d here is negative b, don't worry, you don't really have to know it, all right? Then what it becomes is a plus bi, I've changed the c to negative a, this becomes minus a minus bi, I wouldn't worry about it too much, but what's a plus minus b? Well, what's a plus minus a? Isn't that just a minus a? And this is b minus b. Basically, you get 0. What they're trying to say is that minus a minus bi is the additive inverse of a plus bi, because if you add them two together, you get 0. Now, basically, we regard subtraction as the addition of the additive inverse. So, I wouldn't worry too much about the theory, just know how to subtract. And it's just like you normally subtract, all right? So a plus bi minus c plus di, they're trying to say we don't really know how to subtract. Yes, I know. So what we're doing, we're adding the opposite. You know, when I subtract a number, they're just saying don't subtract the number, just add the opposite of it. So instead of doing a plus bi, I know, minus c plus di, we're doing a plus bi plus minus c minus di. It's a bit, you know. So basically, look here, just go from there to there. Isn't it just a minus c and bi minus di? That's all it is. So, you know what I would just do? What have you got here? Isn't that just 2 plus 3i minus 1 plus 5i? Here we're adding first. So if z1 is 2 plus 3i and z2 is minus 1 plus 5i, find the values of these. So z1 is that, z2 is this. What do I get? 1 and plus 8i. Be careful with the negative one. Next one, z1 is 2 plus 3i minus, I'm going to put a bracket, minus 1 plus 5i. Basically just expand your bracket. What do you get? 2 plus 3i, what do I get now? Plus 1 minus 5i, that's all it is, easy. 2 plus 1 is 3, 3 minus 5i is minus 2i. Now, here, I'm doing a bit of multiplication, 3 bracket z1, so I just go 3 times, I go bracket whatever z1 is. Are we good with that? 3z1, what do you get? You just get 6 plus 9i. Now be careful here, 3i bracket z1. Are we okay with this? 3i, then put your bracket, z1. The reason we need a bracket, z1 is is a complex number and it's got a real and imaginary component. So it's 3i bracket 2 plus 3i, what do we get? 6i plus 9i squared, which we change, 6i minus 9. And whenever you write a complex number, write the real bit first, minus 9 plus 6i. It's got to be x plus yi. Because I squared is negative 1, girls. Okay? Okay. We keep going. So that's adding and subtracting. So we've added, we've subtracted, we've multiplied by a whole number and multiplied by an imaginary number. Multiply, it's just like you're multiplying normal brackets, okay? Basically A gets multiplied by the second bracket and the BI gets multiplied by everything as well. So I'm just going to go straight to the example as you normally would do it. What would you do? 5 times 6 is 30. What's next? 5 times minus 7i is 35i. 3i times 6 is plus 18i. And 3i times minus 7i is minus 21i squared. We need to fix the I squared up. So 3i times minus 7i is minus 21i squared. So we've got, what have we got? 30. What's minus 35i plus 18i? Minus 17i. Now this becomes minus 21 times minus 1, which is plus 21. Therefore, that's equal to 51 minus 17i. All right, remember we're just doing all the basic stuff here today. So next one, if Z1 is 2 plus 3i, Z2 is minus 1 plus 5i. Z1 times Z2 would be 2 plus 3i times minus 1 plus 5i. You can work that one out. And you'd get negative 2 plus 10i minus 3i plus 15i squared. Don't forget to change your... So minus 2 plus 7i, what do we get? Minus 15, which is negative 17 plus 7i. And zi squared, I wouldn't be putting the brackets next to each other. You want to be using a perfect square expansion. So that's 2 plus 3i all squared. Square your 2, what do you get? 4 plus, the middle term will be 2 times 3i times 2. You know 2ab? Yeah, 12i plus b squared is 3i squared. So therefore this is 4 plus 12i plus 9i squared is what? Minus 9. So it's 4 plus 12i minus 9, which is what? Negative 5 plus 12i. As you get better, you can skip steps. Okay? Now, one other thing. Conjugate complex numbers. It's like conjugate surds, similar sort of thing. So, the complex numbers a plus bi and c plus di are called, well, they're not actually conjugates. I think there's a little mistake there. That, cross it out, and a what? Minus bi, fix it up. So the complex numbers a plus bi and a minus bi are called complex conjugates. And we know that if you do multiply them, you will get a squared minus abi plus abi minus b squared I squared, which is plus b squared. In other words, you get a squared plus b squared. So you know what this now gives us? If you multiply a plus bi times a minus bi and you get a squared plus b squared, this is a sum of 2 squares, not a difference of 2 squares anymore. So that means you can factorize it. Now, so if you multiply those two together, you get a squared plus b squared. But if you do the surds, remember this is related to surds. Remember square root of a plus b times square root of a minus b, what do you get? Square root of a times square root of a is a plus b, a minus b. It's of that format. Don't we just square the first one minus second one squared? You just get a minus b. So just notice that the product of a pair of conjugate surds is also a real number. So girls, the product of a pair of conjugate complex numbers is a real number. A squared plus b squared has no imaginary component. Now that's what we use for realizing the denominator. So we've got 3 plus 4i and 3 minus 4i. So let's just do it by a plus b, a minus b expansion. What do you get? 3 squared minus 4i squared. What do you get? So that's 9 minus 16i squared is 9 plus 16, which is 25. So if you multiply the product of a pair of the product of a conjugate pair of complex numbers is a real number. Can you see that? They're complex conjugates. answer's a real number. If if z equals x plus yi, so z is always x plus yi, okay? If z equals x plus yi, then its conjugate is called z with a bar on top. It's called z bar. Is written as z bar equals x minus yi. That's just notation, all right? So if you see z, it's x plus yi. If you then see z bar, it means x minus yi, and we call it z bar. Now we know from the page before that if you multiply z by z bar, you're going to get a real number. You get x squared plus y squared. So x plus yi times x minus yi is x squared plus y squared, because you do a squared minus b squared, right? So the converse also follows when factorizing the sum of two squares. So in 2 unit, you've only learnt to factorize the difference of two squares, a squared minus b squared. Now you can factorize the sum of two squares. X squared plus y squared going backwards, therefore, is x plus yi times x minus yi. So let's do some examples. So it says, for each of the following values of z, find z bar and z times z bar. So here I've got z equals 2 minus 3i. So therefore, what's z bar? 2 plus 3i. And therefore, z times z bar is 2 minus 3i times 2 plus 3i. This is of the form a minus b, a plus b. So isn't it 2 squared minus 3i squared, which is what? 4 plus 9, which is 13. Or 4 minus 9i squared, which is 4 plus 9, which is 13. Okay, be very careful with the next one. Remember, every complex number is x plus yi. What would the x have to be in this complex number? Yeah, it's 0 plus I. So what's z bar? 0 minus I. So therefore, z times z bar is 0 plus I times 0 minus I. Just disregard the zeros. It's just I times minus I is what? Minus I squared, which is 1. Okay. 2. 2's the real bit. 2 plus what I? There's no I. So it's got to be what? 0i. Good. And z bar would be 2 minus 0i. So what's z times z bar? Isn't it just 2 times 2? It's 2 plus 0i times 2 minus 0i. What do you think that's going to be? It's just 2 squared plus 0 squared. It's 4. It's basically 2 times 2 is 4. So the complex conjugate of 2 is just 2. But the complex conjugate of I is minus I. But it's easier once you write it as 0 plus I, then you see the complex conjugate is 0 minus I. All right? Look, 2 really is not complex anyway. 2 is real. It's not, that's not a complex number. Okay? Now, if this is just notation, girls, this is not hard, it's just notation. If Z1 is 2 plus 3i and Z2 is 1 plus I, what is the real part of Z1 plus Z2? What do you think it is? So if you want, we can work out Z1 plus Z2. Let's just work out Z1 plus Z2. What do you get? 2 plus 3i plus 1 plus I. So I'm not putting real, I'm just working out what Z1 plus Z2 is. What is it? 3 plus 4i. So therefore the real part of Z1 plus Z2 is what? 3. That's all it's saying. It's just fancy notation. Now, the imaginary part of Z1 times complex conjugate of Z2. Don't work out the imaginary part first. Just work out Z1 times complex conjugate of Z2. So that's 2 plus 3i times what? 1 minus I. Let's expand it. We get 2 minus 2i plus 3i minus 3i squared. What do you get now? Isn't that 2 plus I plus 3? So it's 5 plus I. What's the imaginary part of that? Yep, it's 1. Positive 1. It's whatever is the coefficient of the I, and it's 1. And the last one here, I think we've done this before. Oh, no, we haven't. Factorize the following. X squared minus 4x plus 13. The way I want you to do it is to first complete... girls, this is not equals 0. I don't have x squared minus 4x plus 13 equals 0. Remember, there's two ways to complete the square. You can either take the 13 to the other side, but there is no other side here because there's no equation equals 0. So when you complete the square with just an expression, and this is just an expression, there is no equals 0. I can't take 13 to the other side because there is no other side. You add and subtract, therefore, from the same side with this type. So I say x squared plus 4x plus minus 4x plus 13 is, actually I might do it here, equals x squared minus 4x. Now, girls, I'm just going to keep the 13 aside. How do I complete the square? Halve the 4 and you get, so I'm going to go plus 2 squared minus 2 squared plus 13. I'm going to keep the 13 there, but I've just gone and, isn't the first line identical to the second? So, I now want to complete the square with the first three terms. X minus 2 squared, what have I got here? Minus 4 plus 13 is what? Plus 9. So that equals that. Now, isn't this, girls, I can't factorize that unless it's a difference of two squares. So that's x minus 2 squared minus, instead of plus 9, I can write it as minus 9i squared. Now that's a difference of two squares, a squared minus b squared. I'm going to rewrite that. X minus 2 squared minus what? What should I put in those brackets that I've just written? 3i. So now a is x minus 2 and b is 3i. Can you see that? So now, how do I factorize a squared minus b squared? A plus b, a minus b. Okay? So I have just factorized that. I'm not solving an equation here, I'm just factorizing that. So the way to do, if you're asked to factorize something like this that can't be factorized, because we can't think of two numbers that multiply to give 13 and add up to give negative 4, it won't work. So we complete the square on the same side. We change the plus here to minus 9i squared. We write it in the form, this is of the form a squared minus b squared, and we know that that's a plus b, a minus b. So notice that there are no real factors here. They're complex. So these are, so basically these are called the complex factors of x squared minus 4x plus 13. Okay? So that's how you factorize that. So you can't say, sorry, can't factorize this anymore. We can. All right. That's it. I will continue from page 8 in the video. You'll get that tonight, hopefully. Oh, yeah, I'll email it. And I'm going to put them all up on BC Online too. Okay? All right. And